So the other day I found this interesting map. This can be found on Wikipedia, and it's very colorful, right? A lot of colors here, and you see these different color regions, and they don't really correspond necessarily to national borders, but there's a lot of them, and they're sort of split up into distinct regions. What does this mean? Well, these actually represent all of the world's synchronized power grids that cover a wide area, that basically are many entities working together to provide a unified, synchronized in time electric power supply. And this is relevant for both current events and for historical reasons. Current event, obviously, is the country of Ukraine, right here. They recently synchronized their power grid to continental Europe. Previously, they were synchronized to the power grid of this, what used to be the Soviet Union, now is Russia and a lot of the satellite countries that were associated with the Soviet Union. Ukraine said, we're going to synchronize with Europe. Now, if you lived in Ukraine or you were there and you had your house powered up, running your lights or whatever it was, you wouldn't ever notice any difference. There's no actual noticeable change, but something definitely changed. They went, and now their grid is synchronized with Europe. So obviously the electricity that we get from the power grid is alternating current. So the voltage of the electricity constantly oscillates. In the United States and in most of North America and some of South America, it oscillates at 60 times per second, 60 hertz, 60 cycles per second. In Europe and most of Asia and Africa, it oscillates at 50 hertz or 50 cycles per second. And the reason why there's two different systems, two different frequencies, is purely historical accident. It's just a product of the development of electricity over the decades in the early 20th, late 19th century, early 20th century, where we ended up with two globally two systems for frequency. And obviously, like I say, frequency implies there's some kind of a timing going on. So when I say synchronize, we can think of it, the best way I can think of it is a band or an orchestra playing musical instruments. So each power plant, each electricity generating facility in all of these regions is like the player in the orchestra or in the band. They are playing the guitar, they're playing the violins, they're playing brass, they're playing drums, whatever it is, and they have to all play at the same tempo, the same beat, or else the music will sound bad. So in order for the music to work, everybody has to be on the same tempo. And the electricity grid is the same way. Everybody has to play at exactly the same tempo for it to work. If somebody gets off tempo in a large power grid like this one here in Russia or in Europe or in the United States, that power station is going to basically experience a severe fault, possibly be damaged if the protective devices don't shut the power station off from the regional grid, because it's like one drummer in a band or one violinist in an orchestra getting off tempo. They're going to be very much singled out by that event. So I'll kind of show over here what this really means, what it actually looks like. So we have here two signal generators, and these generators are each producing about 60 cycles per second. So this would be equivalent to the power that you get out of the wall socket, except it's very low voltage. So we have, this is synthesizing 60 cycles per second, and then this one is doing the same, and they are independent of one another. They do not talk to each other. And we're feeding that into an oscilloscope. And you can see here, this is what this voltage waveform actually looks like. So if you were to take this oscilloscope and measure the power that comes out of a wall socket, electrical outlet, it would look just like this. And the white line is the top signal generator. The green line is the bottom one. They are producing almost exactly the same frequency, like pretty close, like 0.1 hertz within each other. But you can see that the waveforms do not sit on top of each other. They're slightly offset from each other, and we call that a phase difference. So I can actually let this run a little bit, and you can see that in time these waveforms are constantly shifting around. So this would be the equivalent of two power plants generating power independent of one another and not connected together. And the problem here obviously is that you have these are not in time. If you tried to connect these plants together in parallel, which I could actually do that. Let's see what happens if I try to do that here. All right. Let's put a T fitting in and try to wire them up in parallel without being synchronized. Basically what would happen is you'd get all sorts of weird voltages and currents, and people would be shorted out, blown up, have big problems. Okay, there you can see what's happening. It looks like it's completely washed out the green, or the channel 2. Actually, because it's not plugged in. Sorry. My bad. Basically, we're just looking at the channel 1 signal, and this is kind of what would happen to the electricity grid if you connected people together without being synchronized. Your voltages and your lights in your house would be going wild at best, if not the power plants blowing each other up, short-circuiting themselves out with excessive current. So, what's going on here is these countries, or these regions of the world, have decided to make those waveforms so they're perfectly sitting on top of each other, and you don't have that effect that I just showed right there. So how do they do this? So all this green area here, every single power generating plant connected to that grid in Europe and North Africa is singing at the same tune, and their waveforms are exactly on top of each other, playing at exactly the same frequency, so that the electricity is uniform through the entire system. How do they do that? Well, obviously somebody has to start the process, and the way they usually do it is what they call a black start. So there's a few power plants in the system that are designated to basically bootstrap the power grid. So usually they assign that role to a hydroelectric facility because they're very easy to deal with, and they're very good at starting without any kind of external excitation, external influence. So the hydroelectric plant starts up and it energizes all the transmission lines in the area, the big power lines. And then let's say that the next power plant we want to start up is a natural gas fired power station. Now natural gas usually uses what's called a gas turbine. This is basically like an airplane engine, a jet engine, except that instead of pushing the airplane through the air, it turns a magnet, spins a magnet, and the magnet spins inside of a set of wire metal coils, and that magnetic field induces electric current in the coils. So the way that the natural gas plant gets started is they take these coils of the generator in the power station, and they energize them from the transmission lines that are being fed from that hydroelectric power plant. The hydroelectric plant is producing a sine wave pattern like we just looked at on the scope over there, and that basically lights up these coils with electricity, and it causes this magnet to start rotating. It basically turns the generator into an electric motor. Then the generator spins this shaft and starts spinning up the jet engine. It spools up the engine, it gets the turbine and the compressor rotating, and it gets air going through this compressor. The compressor uses the power grid, the power from the hydroelectric plant, to compress the air, and then when everything's up to speed, in the United States, when, let's just say, up to 3,600 revolutions per minute, because that is 60 times 60, 60 cycles per second times 60 seconds in 1 minute, they light the flame in the gas turbine. So they inject natural gas in here, and they fire it off with a spark, and it starts burning and heats up the air going through the gas turbine, and that air then suddenly goes way up in volume and starts putting force on the turbine, and then it actually spins the generator faster than what the grid is spinning it at, and now all of a sudden the power reverses direction, and this goes from being a motor to being a generator. And as this magnet basically was spun up by the signal from the hydro plant, the magnetic poles of the rotor, the spinning part of the generator, were perfectly synchronized with the spinning poles of the generator at the hydro plant. And now all we're doing is we're giving that magnet some torque from this gas turbine, and we're spinning it using energy supplied, mechanical energy supplied from this gas turbine, and now it's producing current that is perfectly in synchronization with what the hydro plant was producing. Now we have a gas plant running at the same time. Then we can take the same process and we can repeat it for the coal-fired plants, we can repeat it for the wind farms, we can repeat it for the nuclear power stations, and suddenly we have an entire power grid with hundreds and hundreds of generators operating, generating, you know, up to as much as 500 billion watts of power. You know, the European Union, you know, their power grid here is probably close to 300, 400 gigawatts. In the eastern United States, we're probably at about 300 gigawatts of power, you know, a third of a trillion watts of electricity. And everybody is exactly synchronized together. Now, all the different colored regions, if you were to take an extension cord and drag it from, say, Colorado over here down into, or let's just say, actually make this easier and more relevant to current events, Texas. Texas, obviously, was in the news in 2021 because it had a major wide area power outages. They started doing load shedding or blacking people out because there wasn't enough generation because of the combination of very high demand and low generation due to freezing generating plants. All sorts of generating plants, gas-fired plants, nuclear plants, wind plants, all had issues with winter weather. So they are their own power grid. They're not synchronized with the rest of the United States or Mexico. So most of their electricity has to be generated within the state. They have very limited capacity to import it from surrounding states. So how does this, what would happen if I was to drag an extension cord from Texas over into Louisiana or into Mexico or into Oklahoma and connect them together? Well, the same thing that happened on this oscilloscope, my light bulb would be going, you know, all sorts of brightnesses and possibly even creating a short circuit condition and drawing excessive current through the extension cord, and causing lots and lots of problems. You can't just connect any of these two regions together directly because the waveforms are not in phase with one another. The orchestra isn't singing the same tune, isn't playing at the same note, and is not on the same tempo as its neighbor is. So obviously, when you look at the world map like this, there's a lot of really interesting questions that come up. And first of all is like, well, the United Kingdom. The United Kingdom is a small, relatively geographically speaking, is a small country, and so is Ireland, and they have their own synchronous power grids, and they're not in phase with any of their neighbors. Do they really, in the United Kingdom and Ireland, rely 100% on their own power generation? They have zero links with the rest of Europe? Is that true? And the answer is no, that is not true. The United Kingdom has power links to France, the Netherlands, Ireland, Norway, and maybe even other places that I'm not aware of. And they can actually transfer electricity to and from all of those regions. But how can they do that if what I just said, if you connected the grids together, they would fight each other? Okay, so this is, there's a little bit of magic. Actually, it's not magic at all, but it is a little weird when you talk about it because it goes against everything we were ever taught in middle school science class about electricity. And that is the use of direct current, DC power. So what did we learn when we were younger about electricity? When it was discovered and it was commercialized, there were two distinct people that were involved. There was the Westinghouse or the Nikola Tesla side of things, and there was the Thomas Edison General Electric side of things. And they were said to be at war with one another, and they had two completely incompatible systems. And in the end of the day, the Westinghouse Tesla alternating current system prevailed because alternating current is more efficient. It can be sent over longer distances. That's what we were always told, right? That's the mythology that surrounds alternating current. But it is not the fact that the current is alternating that makes it special. What makes alternating current special is a special device called a transformer. Transformers are why the Tesla/Westinghouse system won the war of currents, because this allows voltage to be changed without any moving parts. So if I have 120 volts here on this side of the transformer, I could have 7,200 volts on the other side of the transformer. And this magnetically links the two circuits together and allows you to use very, very high voltages to transmit electricity long distances. So the transformer enabled the use of high voltage, and high voltage allows you to transmit power with very low losses, because the thing that determines how much electricity is lost on a wire is the amperage, or the current, not the voltage. So the higher the voltage is, the lower the amperage for a given amount of power, and you have less loss. It's actually it's a very dramatic effect. The voltage, the power loss goes down with the square, or the square of the voltage. So if you double the voltage, your power loss goes down by a factor of 4. It's squared. That's a major, major advantage of high voltage. But obviously, 7,000 volts in your house is not something you want to be dealing with. A lot of risks and safety issues with that. So we step it down to 120. So if I look out here on the power pole in front of the house, there is 7,200 volts up on the wires up above, but it steps it down to 120 for us to be able to use inside. 120/240. There's actually two separate 120 volt lines coming into your house, and you can add them together to make 240 to run your dryer and your stove and all that stuff. So the transformer enabled high voltage, and high voltage is why AC prevails, because DC can't be transformed using this kind of device, and it was limited to the same voltage being used as was generated. So when Edison was generating power in New York City at Pearl Street Station, he was generating at 110 volts. And by the time that voltage got through the four-arm thickness cables to the buildings with the light bulbs in it, the voltage had already dropped 10%, and it was down to like 100 volts. So that was a big, big problem for the DC Edison system, because the voltage was too low, not because it was DC. So what that means is that DC is not the inherent problem, and DC is how the United Kingdom and Ireland transmit electricity to all of its neighbors. It's how New Zealand can transmit power between its North Island and South Island. It's how Texas can move power between Mexico, the western U.S., and the eastern U.S. It is how all of these different synchronized grids can transmit electricity between each other, because they can take the power on one grid, convert it to direct current, to DC. So let's just say it's UK, convert to DC, send it under the English Channel to France, and then France takes that DC and converts it back to AC and synchronizes it electronically with their continental Europe power grid. So you have UK, all right, they convert their AC power and they convert that to DC. They rectify it, okay, using electronic components. All right, rectify it. And they send it under the English Channel. They send it over to France, and then France uses more electronic components to chop it up back into AC, inverters as they call them, and go into its local power grid synchronized to the rest of Europe. So the advantage of this DC going under the water, there's a lot of things about it that are beyond the topic here, but this has very low losses when you send a direct current at high voltage, and there's actually a name for it. They call it HVDC, high voltage direct current. And high voltage direct current is used anywhere they need to transmit a lot of electricity a very long distance. There's actually HVDC lines all over the place, even within these power grids. So out in the western United States, there's actually HVDC lines that run from Southern California up to the Pacific Northwest, because the Pacific Northwest has a lot of hydropower, and they can share that with Southern California, but the distance is very long. You're talking 500 miles. So they can transmit that power with extremely low losses at a voltage of like plus and minus 500,000 DC, which is actually equivalent to 1,000,000 volts of direct current. 1,000,000 volts means you can send gigawatts of power with like 1,000 amps through wires that are probably a couple inches in diameter or something like that, for 500 miles with very, very low losses, like much less than 5% loss, maybe even like 1% loss, or whatever it is. Okay, so HVDC enables that to happen, and even in Texas, they will have HVDC that takes the synchronized grid of Texas and links it right across through a very short DC line to, say, Oklahoma or Mexico or one of its other, neighboring states. And that kind of is how it's done. Just check my time here. So we have a couple other interesting things that go on in the world with this stuff. So Japan, little tiny, obviously Japan is, geographically a small area. But Japan has two separate grids, right? They show separate colors. And when I showed the two frequencies that were incompatible, that were the same 60 hertz but didn't link up in time with each other, Japan actually has both 50 hertz and 60 hertz in the same, obviously in the same country. So you've got the western part of Japan, down kind of like where like Hiroshima and those places are, down here, that is 60 hertz, and then Tokyo is 50 hertz. And that is purely because of the history of the utilities in those areas. Up in the northern or eastern part of Japan, they were purchasing equipment from European companies. The western part, they were purchasing it from American companies, and we ended up with two incompatible systems. And in order for them to talk to one another and transmit power between them, they have to use DC, convert from one frequency, from 50 hertz, to DC, and then to 60 hertz or vice versa, to get it to go across the borders. Means that in the same country you have power plants that are running at 60 hertz and you're running at 650 hertz within the same national boundary. There's probably one more that I'll talk about that's even more bizarre than Japan. And that is in South America, down here in Brazil and Paraguay. Brazil and Paraguay have a thing called the Itaipu Dam. Alright? Itaipu is a 14 gigawatt, 14 billion watts. That is 7 times the size of Hoover Dam. That is equivalent to about 14 nuclear power reactors. That is a very, very big hydroelectric power plant in Brazil, on the border of Brazil and Paraguay. So there's a river, obviously, that defines the border of those two countries, and this Itaipu Dam is on that river. And Itaipu is set up, so I said it's 14 gigawatts. There are, I believe, 20 generator units in the Itaipu, something like that. I think it's 20. Let's just say it's 20. I think there's 700 megawatts apiece or whatever. So we got Itaipu, we got the powerhouse. All right, the river goes through there, and the river's going through the middle here, and each side has generators. There's 10 generators on each side, right? And this is Brazil over here, and this is Paraguay over here. 10 on Paraguay's side and 10 on Brazil's side. Okay, that's fine. No big deal. But Brazil uses 60 hertz. Brazil shares the frequency that we have here in the US, whereas Paraguay ended up with 50 hertz. So the 10 generators on the Paraguay side of Itaipu operate at 50 hertz, 3,000 RPM, or whatever speed they're running at. And on the Brazil side, the 10 generators operate at 60 hertz. Okay, well, each country wanted its own set of generators that was compatible with its national grid frequency. And as you can see, they are not the same synchronized power grid between Paraguay and Brazil. What is interesting here is Paraguay is a fairly small country. I forget which one it is. It might be this one right here. But Itaipu is generating 7 gigawatts per side. So there's 10 700 megawatt generators. on each side, 7 billion watts. Paraguay cannot use all 7 billion watts. This single power plant generates more electricity than the entire nation of Paraguay requires. Whereas Brazil can, this is a smaller supply for Brazil, because Brazil is a large country with a lot of people. So, up above here someplace, there is a converter station, all right? And they convert 50 hertz power from the Paraguay side of the Itaipu Dam into 60 hertz power and sell it to Brazil. Interesting, right? So they didn't, when they built this thing, they didn't decide, well, Paraguay only needs, say, 3 gigawatts, so we're only going to put 3 or, whatever number of 50 hertz generators in and then just make the rest of them 60 hertz. They split it up evenly, 50 hertz, 10, 60 hertz, 10, and whatever Paraguay can't use, we convert to DC, then convert to 60 hertz, and then Brazil can buy that. Now, I believe they also have the ability to sell some of the 50 hertz into Argentina, which is a 50 hertz country. So, that's it. And a lot of interesting stuff here. The United States, like I said, split up into Eastern Interconnection, Western Interconnection. Texas, there's also Quebec has its own power grid that is not synchronized to the rest of Canada or the US. Scandinavia has its own power grid. The Baltic countries of Estonia, Latvia, and Lithuania are their own synchronous power grid. Korea, South Korea is its own, and it's separate from North Korea, which is separate from China. And India looks to have its own, at least one, if not 2, synchronous grids. Middle East, there's a couple of them. And then Sub-Saharan Africa, they don't have a unified wide area power grid, but all of the electric utilities and all of the different regions of Sub-Saharan Africa operate their own independent local power grids. Same thing with like Thailand and some of these places that are very sparsely populated, like the Northern Territory in Australia, Greenland, things like that. So that's the world of synchronous power grids, making sure that the sine waves mesh over top of each other so that you get a consistent voltage through the entire system, and that all the generators are singing the same tune. That's it.